Welcome back to the Deep Dive. Today we are wrestling with, I think, one of the most fundamental and frankly confusing questions in AI.
Hmm.
Can large language models actually reason?
It's the million-dollar question, isn't it? I mean, LLMs are stunningly proficient in language. They can write poetry, they can code, summarize complex topics.
Right.
But that high language capability, it often masks a core tension. When you get down to the brass tacks of drawing reliable inferences from premises, they often stumble.
And that's the key distinction, right? If you go back to the philosophical foundation, specifically epistemology,
Hmm.
the philosophy of knowledge reasoning is defined precisely as that. The
Exactly.
ability to draw robust, reliable inferences from evidence. It's what lets us solve novel problems, not just, recite things we've seen before.
Exactly. It comes naturally to us, but for AI, it's a synthetic skill. We saw
Yeah.
those early flashes when GPT-3 first emerged, showing hints of it with logic puzzles. Then, when ChatGPT and GPT-4 arrived, their performance across structured benchmarks, I mean, from legal exams to advanced math, it was state-of-the-art. And that's what triggered all the excitement.
That's where all the sparks of AGI talk came from.
Yes, the claims that we were witnessing sparks of AGI, artificial general intelligence.
The initial results, they certainly looked like genuine reasoning. But as you mentioned, almost immediately, researchers started running diagnostic tests and found something, well, surprising.
They did. They found that while the models could emulate reasoning perfectly on simple tasks, the underlying mechanism was often just pattern matching.
Or statistical fluency, not reliable,
Yeah.
step-by-step logic that actually generalizes.
It's the difference between memorizing a formula and understanding the math behind it. If you change the context even slightly, that statistically fluent model often just collapses.
So that is our mission for this deep dive. We're pulling back the curtain on the actual research, trying to bridge that profound gap between language ability and genuine, reliable inference.
We'll start with the clever tricks deployed right at the moment of asking a question. Look at how researchers are fundamentally retraining the models.
And finally, reveal the architectural breakthrough that allowed these systems to solve problems over millions of dependent steps without a single error.
Let's start where the journey really began, prompting. This falls under the broader category of test time compute.
Okay, let's unpack test time compute, TTC. So it means improving the model's output during deployment.
Right, without having to spend billions retraining the base model.
And the foundational technique here was chain of thought, or COT, prompting. It was revolutionary.
It was a true holy cow moment in the field. Before COT, the prevailing wisdom was that you just had to make the model bigger to get better results.
Right, more parameters.
COT showed that you could take an existing model and drastically improve its reasoning just by adding a few simple words to the prompt, like, let's think step by step.
It sounds almost too simple.
Hmm.
How does forcing the model to write out its work actually improve its logic?
By decomposing a complex problem into these manageable linear steps, you're effectively scaling up the model's internal compute for that specific moment.
So instead of trying to jump from the question to the answer in one leap,
Exactly. It's forced to slow down, check its intermediate findings, and allocate tokens to the process. It's like asking a student to show all their rough work.
okay, so once that linear approach proved so effective, I imagine researchers realized that simple straight-line thinking wasn't enough for really complex problems.
Precisely. They knew they needed to scale up that inference even further. That's when the branching methods came in.
We moved beyond linear COT.
Very quickly, we moved to methods that explored multiple pathways at the same time. The first major generalization was tree of thoughts, or TOT.
So TOT sounds like a choose-your-own-adventure book for the model.
That's an excellent analogy. You start with the problem, and then at each step, the model doesn't just pick one path. It explores several possibilities, or branches.
And it generates multiple potential next steps.
Yes. And then it assesses those branches using an internal score, a heuristic, to determine which path seems most promising to reach the goal. It just massively increases the search space for a solution.
But the downside of a tree, I guess, is that you always have to move forward, right? You can't connect two separate paths that ended up reaching the same useful conclusion.
And that's what birthed Graph of Thoughts, or GATI. GATI extends the structure further, moving beyond simple trees to allow for arbitrary connections between reasoning units.
So you can have merging steps.
You can have merging steps where two different lines of thought converge on a single realization, and you can even have reasoning cycles, allowing the model to refine a belief over and over.
Okay, so if TAT is exploring different options, GOT is allowing the model to act more like a research team,
That's a great way to put it.
where two different scientists might approach a problem differently, but they realize they both found the same key piece of data and decide to merge their efforts.
That's spot on. It allows for a much more sophisticated aggregation of knowledge. And the most elegant way to leverage these multiple paths isn't just to pick the best branch, but to use a technique called self-consistency.
Tell us how that redundancy works.
Self-consistency is, it's statistically powerful. Instead of relying on one single reasoning path, you tell the model to sample many different paths, say 10 or 20.
And each one could lead to a different final answer.
Potentially, yes. Then you just select the final answer based on a simple majority vote. By aggregating results from multiple attempts, you significantly reduce the reliance on any one single, potentially flawed path.
That feels like borrowing reliability from the sheer quantity of computation. Now, beyond just internal sampling, we also saw frameworks that brought external feedback into the prompting loop.
Yes, this is when the model started becoming integrated with their environments. The famous example here is React.
React.
It's a framework that interleaves reasoning, which they call thought, with action, which is interaction with an external tool, like a search engine or a calculator.
So it provides grounded, verifiable reasoning. The model realizes it needs to stop thinking internally and actually go do something to check the next step.
Exactly. And even more fascinating is the self-critique loop used in systems like Self-Refine. Here, the LLM generates an answer, and then immediately after, the same LLM is prompted to generate natural language feedback on its own initial answer.
And then it uses that feedback to refine the original answer iteratively in a loop. It's the model acting as its own editor and proofreader.
That's it.
So what we've established is that external orchestration smart prompting, generating multiple paths using tools, can take existing models and greatly improve their reasoning. But these are still clever tricks.
Right. They don't actually change the model's internal knowledge or capacity. They only orchestrate what's already there.
That's the critical limitation. You
Yeah.
can only prompt a model so far. If you want a truly fundamental improvement in reasoning, you have to internalize that capability.
You have to update the model's weights. And that shifts us squarely into the realm of training-based methods.
And this is where reinforcement learning, or RL, steps up.
It is. In this context, we treat the LLM as the agent. The goal is to train that agent to interact with an environment, a sequence of logical steps, to maximize a cumulative reward.
So the system is selecting the optimal reasoning policy.
The sequence of steps with the highest expected reward, yes. Under the hood, this often uses methods like policy optimization, specifically PPO, which is a popular algorithm used to get that optimal strategy by adjusting the model's behavior based on the rewards it gets.
I think the most critical distinction here is how you reward the model for thinking better. You can reward the outcome, or you can reward the process itself.
That's the core debate in reasoning training right now. You have outcome supervision, which offers what's called a sparse reward. You only check the final answer.
If it's correct, you get a 1. If it's wrong, you get a 0. It's just grading the final test.
Exactly, which is very simple to implement, but doesn't tell the model where it went wrong if it failed. But interestingly, we've seen models that rely primarily on the sparse reward achieving spectacular results. For example, DeepSeek R1, which is a massive mixture of experts or MOE model with 671 billion parameters,
Wow.
has shown superior performance in certain benchmarks, which challenges the view that process supervision is always superior. Sometimes outcome is enough if the model is big enough and the data is rich enough.
Still, process supervision seems inherently more aligned with how we teach humans to think.
It absolutely is. Process supervision provides a fine-grained reward signal. Instead of just grading the final answer, you reward each intermediate reasoning step based on its relevance to forming an optimal chain.
It's the difference between grading the final test and grading every single step of the student's homework and rough work.
That's the power. By rewarding the individual steps, you guide the model toward a more coherent final answer, ensuring the path is logical.
Which would help it avoid going down tangential paths early on.
Absolutely. And this approach yields significantly superior performance on highly complex multi-step math tasks, like the specialized math dataset.
The cost of that fine-grained data, though, having humans label every single step of a complex problem as right or wrong, that must be immense.
It is. And that cost drove researchers to look for ways to automate the labeling process. That's where techniques like STAR self-taught reasoning came in.
Okay.
STAR essentially bootstraps its own training data. The model generates rationales for a problem, filters only those rationales that lead to the correct final answers, and then fine-tunes itself on this huge new data set of self-generated, proven correct reasoning.
So it dramatically cuts down the need for costly human labeling.
Exactly. And when you combine that massive scale RL training with a highly specialized architecture, you get results that were, well, unthinkable just a year or two ago.
These are the dedicated reasoning models.
Yes, the culmination of this work. We saw this clearly with models like OpenAI's O1. This model was trained specifically using large-scale RL to perform extended chain-of-thought reasoning, resulting in the generation of these lengthy reasoning tokens before the final answer.
How does that dedicated training translate into actual performance gains?
The comparison data is truly staggering, and it shows the monumental advantage. On the American Invitational Mathematics Examination, or AIM, which is a notoriously difficult benchmark, the specialized O1 model achieved 74% accuracy with single sampling.
74%.
Now compare that to the 12% accuracy achieved by its general-purpose contemporary GPT-4o when using standard prompting.
That's a huge difference.
That is a 517% relative improvement. It's a compelling argument that the path to true intelligence requires these specialized training loops, not just scaling up the pre-trained general model.
So we have models that are over 500% better at complex reasoning because of smart training. It sounds like the problem is solved. We prompt them cleverly, train them intensely, and we should be ready to hand over organizational problems.
That's what everyone thought. But the gains, as significant as they are, ran headlong into an immutable mathematical wall. Despite all these advances, the smart prompting, the deep training, a fundamental catastrophic limitation persists in any single-agent system.
The critical barrier.
Yeah.
The mathematical reality of failure in long-horizon tasks.
Exactly. Every single LLM, no matter how advanced it is, exhibits a persistent per-step error rate. Let's call it P. And that persistent error rate, even if it's tiny, kills long-horizon tasks.
It's like a massive assembly line building a satellite. If one single component is flawed, the whole thing fails.
Perfect analogy. The entire $100 million satellite fails.
So for you listening, we're talking about exponential decay. You don't just add up the errors. They multiply the potential for failure at every single step.
Precisely. If a task requires, say, n sequential steps, the success probability is determined by multiplying the chance of success, 1 minus the error rate, by itself n times. The probability of failure grows exponentially with the length of the task.
And the consequence is just catastrophic failure once the task gets long enough.
Yes. Let's make this concrete. Even if you manage to push that per-step error rate down a fantastic 0.01 to a 1% error rate per step.
Which sounds great.
It sounds amazing, but the probability of successfully completing a task still drops below 1% after just 500 dependent steps.
Wow.
That's because the expected number of steps before the first inevitable error is just 1 divided by the error rate. If your error rate is 1 in 100, you expect to fail after about 100 steps.
And we have empirical proof of this performance collapse. I remember seeing studies using controlled environments like the classic Towers of Hanoi benchmark.
Yes. Those studies demonstrated that state-of-the-art single-agent reasoning models inevitably failed beyond approximately a few hundred steps. You just hit that mathematical wall, and no matter how much more you prompt or train, the system breaks down.
The takeaway here is vital then. The single-agent path, no matter how impressive the individual model is, it just can't reliably handle organizational scale problems.
Not the ones that routinely involve thousands or millions of dependent steps. If we want AI to manage complex processes, the model structure itself must be fundamentally different.
Okay, this brings us to the breakthrough, the architectural solution that finally sidestepped the error propagation problem. We're talking about massively decomposed agentic processes, or MDAPs.
This is the paradigm shift. We stop trying to optimize the individual agent and we start orchestrating collaboration to ensure collective reliability.
The key idea is borrowed directly from engineering.
It is. Ensembles of models can achieve vastly greater reliability through coordination mechanisms like redundancy and majority voting.
Because if you have multiple independent agents working on the same subtask and they vote on the result, the voting error rate decreases exponentially as you add more agents.
This is how human organizations achieve reliability despite individual human flaws. And this is precisely the foundation of the Maker framework. It's often called the million-step solution.
Okay, tell us about the mechanics of Maker. If this error propagation wall is inevitable, how did they push through it and achieve that level of reliability?
They employed two core principles. First, extreme task decomposition. Instead of asking one powerful agent to handle a complex task, they broke the task down into the smallest meaningful units possible.
Microtasks.
Microtasks, yes. That could be addressed by highly focused microagents.
It's the ultimate division of labor, like building a city block by having one person mix mortar, another lay just one brick, and another check the level.
Exactly. And the second principle was multi-agent voting applied at every single junction. Multiple microagents process that tiny subtask, and their outputs are immediately aggregated through voting to ensure correctness.
So that voting acts as an immediate continuous error filter before the system is even allowed to proceed to the next step.
That's it. Every step is checked and corrected before the error has a chance to propagate. It sounds computationally heavy, but functionally, it's almost perfect.
And the result was unprecedented.
It was. Using this maker architecture, they demonstrated the capability of solving those long-horizon planning tasks, specifically the Towers of Hanoi benchmark, with over 1 million LLM steps with 0 errors.
0 errors over 1 million steps. Where the previous state-of-the-art models collapsed at just 500, that's a fundamental change in the trajectory of AI reliability.
It suggests that the path to massive organizational scale problem solving lies not in waiting for a single flawless AGI, but in designing distributed fault-tolerant architectures and orchestration layers.
The intelligence is distributed, and the reliability comes from the system design.
Precisely.
And we're seeing this play out in the real world already with coordination frameworks. You mentioned AutoGen and MetaGPT.
Absolutely. MetaGPT, for instance, uses roles like product manager, architect, and engineer mirroring human SOPs and structured workflows to manage multi-agent coordination. It shows that the key to AI scaling isn't just raw intelligence.
It's the power of structured workflow and the division of labor.
Exactly.
What an incredible journey we took today. We started with the simple linear prompting of chain of thought, moved through the highly specialized reinforcement learning that created reasoning superstars like O1.
Only to smash headlong into that immutable mathematical wall of error propagation.
And the solution wasn't smarter models, but smarter systems.
That's the core synthesis. The success of massively decomposed agentic processes suggests that the path to solving truly massive, long-horizon societal and organizational scale problems, the ones that routinely involve millions of steps in fields like logistics or resource planning, it lies in designing these distributed, error-correcting architectures.
It means we have the technical roadmap to build reliable AI organizations, not just reliable AI individuals.
That's right.
Which leaves us with this final provocative thought for you to chew on. If LLM systems can now reliably execute complex processes involving 1 million sequential dependent steps, what is the single most complex long-horizon organizational process, maybe in global supply chain management, complex medical diagnostics, or adaptive energy grid control that you think an AI system could manage successfully by the end of the decade? We'll leave you with that question.